Okay, folks, let's get going. I think many of you would have probably seen the post that, and hopefully you've listened to the last week's recording. We chose through voting, the Rainforest Connection audio detection competition. Um, so that's the competition we'll be focusing on over the next several weeks, possibly months. And I think Steve went through an overview of it last week. That was pretty good. And hopefully you had a chance to listen to that. If not, we'll again spend some time looking at the basics and doing some exploratory data analysis type of stuff before we get into all the details and the various approaches and possibilities. But before we proceed, since there are a couple of new people, just wanted to make sure are each of you able to at least enroll in the competition and enroll in Kaggle and have things set up to where you can run notebooks if you wish related to the competition, or are you experiencing any challenges with that? Anybody having any issues, then I would welcome them to speak up. We want to accommodate people with all skill levels. So if you're experiencing any challenges, let us know here or on Slack. And there are enough people who have done this before to where we can respond appropriately. That said, anybody made any attempts or want to share anything that they were able to do in the previous week?
I haven't had a chance this week to do anything on the competition. So apart from just taking one of the basic notebooks that I did 2 weeks ago, just to check that we could submit okay. Yeah, it's my only submission, so I haven't done anything this week further yet.
Yeah, and actually, I mean, I think last week you kind of took people through kind of what are the files and taking them through. So that, at least to me, was very helpful as I went through the basics to get an overview of the competition. So thanks for that, Steve. And we'll again spend more time on that this week as well. Just getting, because sound is something that at least I have not dealt with. I don't know if anybody has much more experience dealing with it. I encourage them to speak up and share their experience, but sound is new. So at least today, I'll just be sharing when we get to it, multiple links and thoughts, and I would say kind of going through the basics of even sound. And despite being an electrical engineer, it's the sound processing is buried way deep in my brain cells that I can hardly retrieve them. So it's good to get a refresher on that as well. Anybody else want to share any attempts they made or played with any EDA stuff of the or existing notebooks or their own attempts, anything of that kind?
I did the same as last week. Steve posted the EDA, just managed to submit it, but that was pretty much it. So nothing new I did. So the basic one.
Okay, thanks, Dinesh. Anybody else? Okay, if not, what I thought I would do is just kind of the metric for this competition is fairly unique. So I thought I would spend a little bit of time I think Steve last week pointed to that. I wanted to take a little bit more time and kind of go through the calculations and what it's trying to achieve. There are still some questions that I'm not that I still don't have the answers for. Maybe as a group we can learn more about it. And again, just to emphasize, part of the reason we do this on ended competition is so we can share knowledge and notebooks and things like that, and not be restricted by Kaggle. The other thing, at least I like to do, is if you're processing sound or something unique, I like to take the opportunity to kind of learn about it, learn the details of many things along the way, and not just kind of jump to, hey, here are the best notebooks, or let's just kind of submit and get the best score and away we go to the next competition. Kind of learn the key things or the key principles of the domain area as well. So with that said, I wanted to spend some time on the metric, which is this label weighted label ranked average precision, and then also spend a little time pointing to different resources that I spent time looking at. Even I wasn't even able to finish going through all of that, but just pointers to the various resources that I was looking at from a sound processing and the basics of sound and why frequency domain and what is basics of Fourier transform and things like that. That if you're interested, still you can spend a lot more time than I did going through it, but at least share some pointers. If anybody else has anything that they feel is more relevant or appropriate, please feel free to jump in and share that now. Anybody have anything they want to share and feel is important? If not, I'll move to sharing what I have. Anyone? Okay, if not, let me see whether I can share my screen. Let me know if you can see my screen.
Yep.
Okay. So, Steve, since you went through it, did you spend any time on kind of getting a better understanding of this particular thing and would like to speak to it? Otherwise, I can go through it myself.
All I really did, like that Stack Overflow article that you have there in front of you. Yeah, like I basically just sort of read through that myself and found that to like be a pretty good introduction to like this loss in the competition. Yeah, so like it's a good way to understand what's going on in the sort of multi-label type of loss.
Yeah. So with that said, let's just go through it. At least this particular example, I think, gives us the mechanics of how to calculate what is the metric that's being used to judge our results in the competition. And what is also interesting is the scikit-learn implementation that I'll point to once we go through this, after we've gone through this, is actually one step shy of what is actually used by the competition. Because the scikit-learn implementation, and this will become more clear as we go through the detail, is sample-based average, whereas the first two words of the metric, label weighted, label ranked average precision, tells us that in the competition, the weighting is done by the totality of the labels and not by the samples. So that's the difference between what's actually the implementation. It's just one additional step beyond what scikit-learn implements. So it's fairly, just probably a line of code if that to change it from what scikit-learn has to what we need, but that's important to know. So we'll go through the mechanics of it, and then I'll also share the question that I've been pondering that I don't have a convincing answer for. Maybe people can chime in and maybe we'll collectively get to the right answer. But the mechanics. So let's say we have three items that we want to label: cats, dogs, birds. And then if we have images in which these three things can appear, and then the ground truth will be as it is here. Now, keep in mind that this is not one hot because there are multi-labels, so it could be multiple ones. So in this case, because there is just one cat image in it, it's 100. So, and then we go through and eventually our model outputs probabilities, and the probabilities are these values, 0.9, 0.2, 0.3. The first thing we do in order to implement this metric is we rank order the probabilities. That's very important. It's kind of step 0. So if we rank order it, then you can see that what will happen is, now keep in mind that this probability is in the order of cat, dog, bird. So CDB. So cat, dog, bird. Then the cat got first place, bird is second, dog is third, right? So cat, then dog, then bird. But when we rank order it, then bird actually gets the second place because its probability is higher. Now, the mechanics. We count how many labels it takes to get to the class of interest, which in our case is cat, because there's a cat in the image, and starting at the first place. And because cat is already in the first place, so it's basically we start at 1 and cat is at the first place, so our answer is 1. That's the first value we calculate. Okay, so that's value 1. Now, next step, remember the 0th step is rank ordering. The next step is calculating how many labels it takes to get to the label of interest, which in our case is cat. So that's in position 1. So that's 1. Then the third step is we count how many other true labels there were until we reach the correct label. And this may seem confusing, but we'll get to multi-label examples and that'll make it clearer. But in this case, the cat label is the correct label and it is at the first position. So again, the answer is 1. So we don't need to move any further. So it's again 1. So now the score is calculated by taking the second value that we get, which is this one, divided by the first value we calculated, which is 1. In this case, both are 1. So it's 1 by 1 is 1. Now, what happens if the model gets this thing out of order? So that's what makes this kind of metric a little bit interesting, because the ranking seems to matter, right? Rather than just how many or what we got right or just the precision. So, so that's why it's label rank precision, label ranked and average precision. And then, so now let's say some other model, it outputs this value. So now remember, cat is still, this thing is still cat, dog, bird. Now, dog is point. So when you rank order it, then you're going to get dog, cat, bird, right? So dog got first place, cat is now in the second place, and bird got third place. So again, we go through the same. So first step, we have ranked. So that's why we say 0.8, 0.61. So that's how we determine that, dog is in the first place, cat is in the second place, and bird got third place. Now, again, repeat these second and third steps. So the second step is how many labels does it get to get to the true class of interest? So now the cat is in the second position, right? So starting at first, so it takes 2 labels. So the first value is 2. The second thing we need to figure out is how many correct labels there were along the way. And there was only 1 correct label along the way. So the second value is 1. So then remember that we do the second divided by the first, and therefore the value is 0.5. Now, these are simple exercises, but we'll get to, again, a little more complicated examples to help us get a fuller understanding of the metric. Same methodology applied when you have two labels. Okay. Image contains, now the image doesn't contain just one thing, but it contains, let's say, two things. So, and that's why in this case, for example, two labels. So, when we did the second part and got one, it's because there's only one correct image in the ground truth. In this case, there are two correct images in the ground truth. It contains a cat and a bird. And the model outputs this. So the ranking is bird because it's 0.9, then cat for 0.8, and then the dog in the last place. So for the cat label, the first value is, remember that now it took us bird and then cat. So it's 2 because it took two labels to get to it. The second value is 2 again. Why? Because there are two true values in the ground truth, and we passed the first true value and then got to cat. So by the time we get to cat, there are two true values. So that's why the second value is 2. And so the second divided by the first still gives us 1, right? And you do the same thing for bird. The first value is 1 because the bird is in the first position. And the second value is also 1 because we just get to bird in the first step itself. So again, it's 1. Okay. Now let's say incorrectly ranking.
Can I interrupt on this case? So the model output is 0.8, 0.2, and 0.9.
Correct.
So 0.8 is for a cat. Why it's saying ranking is bird, cat, and dog?
Oh, you rank based on the probability values that it gives, and 0.9 is greater than 0.8, right? So it's saying that the probability of finding a, in this case, what is the probability of finding a bird is higher in the image than the probability of finding a cat.
Okay.
So you see that? 0.9,
Yeah.
0.8, 0.2. So that's why the rank ordering is first done based on the probabilities that your model outputs.
Okay. Okay. Yeah, got it. Thanks.
Okay, and then, so let's say incorrectly ranking two labels. So image contains a cat and a dog. So cat, dog, bird is the thing, right? So cat and dog, the model outputs this, which means it says bird is the highest rank, then dog, then cat, right? Whereas the image actually contains a cat and a dog, but it's incorrectly saying bird, right, is the highest probability, then dog, then cat. For the cat label, right, the first value is 3 because in order to get to cat, 1, 2, 3, we're getting to the third. And the second value is 2 because there are two true values that by the time we get to cat, the dog and the cat, because that's the ground truth values, right? So then you divide the second by the third, which is 0.66. And you do the same thing for the dog, the same way that I just explained, you calculate it. And so the first value is 2, the second value is 1, so we're going to 0.5. Now, the interesting thing is, how do we get to the, having done all this, how do we get the final score for each class, that is for each of cat, dog, or bird? How do we get to the final score? The simplest way would be to take the average, right? So let's use the previous two examples to calculate this. So for cat, we had scores, if we go back and look, for cat, it's 1, right? And then in this case, the cat value is 0.66. You see that? Meaning the first one, it got a 1 for the cat. And then in the second one where it was incorrect, it was 0.66. So think of this as one sample and think of this as the other sample. So you now have a score of 1 for the first sample and then 0.66 for the second one. So final cat score is 1 plus 0.66 by 2, which is 0.83. Now for dog, 0.5. So final dog score is 0.5 because there's just one instance, if you will, of the dog between these two samples. For bird, again, 1. So the final bird score is 1. Now, the metric is great for analyzing class performance, but this is per class. But what if we want a metric for how good the model is across all the classes, right? That's kind of what we want. So we want to compress it into one final score. So we could just average all of the final class scores, right? Which is average all of these class scores. So 0.83 and then 0.5 for dog and bird 1. So, but if we just average it, then here's what happens. As we know already, this would dilute scores of the common classes because you would have to divide by the, or they appear more often, and boost the less frequent classes. Now, to avoid this, what we do is use a weighted average. So using the two example images, meaning the two samples, we now have 2 cats, 1 dog, 1 bird. So what we do is say 2 cats, and this is where the label weighted label rank comes in. So the label weighting is because we weight by the labels of the classes. So 2 cats, and the total of labels is, remember, 2 cats, 1 dog, 1 bird. So there is 4 labels total across the 2 samples, but there are 2 cats across the 2 samples. So you do 2 cats by 4 labels times 0.83, 1 dog by 4 labels times 0.5, and 1 bird by 4 labels times 0.1 is 0.79. Now, interestingly, conveniently, this ends up being the same as averaging all of the individual scores. So we don't even need to store the class weights, right? Because we had scores of 1 and 1 for the cat and the bird for the first image, and then 0.66 and 0.5 for the cat and dog for the second image. So if you just add these and divide by 4, which is the total number of labels, then you'll get the same value as what you got by doing the weighted average based on the dividing by the total labels and the examples of the classes, right? So this is the mechanics of how you go about calculating the label weighted, and the label weighting piece comes from this part here, and the labeled ranked average precision is all you have calculated up above. Okay, so that's at least my understanding of what the mechanics are. Then it would be easier for you to either code it yourself or even understand the code that you see being used. But now I have a question which at least I have the semblance of an answer for, but I was just wondering because I did some search, found some explanations, but not really great ones. So the question I would throw out is, why would you go about using this metric compared to any other metrics that we've seen so far? Why is this metric being chosen for this competition in particular? Any thoughts?
Is it not just a good way to like measure the performance when the image can, well, the soundscape can contain multiple classes?
Yes, but the micro macro averaging type of stuff that we've seen before of multiple classes also does it, right? So why label ranked average precision? Like, for example, Steve, when we went through, I don't know, the very first competition of just classification, simple multi-label classification of, again, 29 classes, I think, of some, I forget now what it was, but something in cells, some kind of bodies in cells that we were supposed to rank.
Yeah.
And we just did a micro averaging or a macro, I forget now, but the micro and macro averaging. So why is that metric, or what are, or we can ask it in a different way, when would you choose this metric, or when would you choose the other one, or why this versus the other? And we have seen multi-label classification in, at least I'm trying to think whether there were other instances of multi-label where we've used slightly different metric. I mean, I agree, it's a good metric. I'm just a good metric, but I'm just wondering why this particular metric as opposed to other metrics like, just micro class averaging or macro class averaging and things like that.
I still don't get, I can't get my head around completely what exactly the mechanics are, but at a very high level, I feel it like matters if you're like in the same species of the birds, maybe they sound close enough. So maybe rather than saying they're completely off, getting the species itself wrong of which bird you're predicting, there is more value of predicting something of the same species rather than predicting something completely off. Whereas in the previous example of where you were seeing 29 examples, those are like, I don't care if you predict anything else and can be wrong, but there's only one thing right. But here there is, I feel like there is some value, like even if you predict the right thing at the second place.
Partly I agree with you, Rekhan, but it isn't, in this case also the species are 24 and there isn't like a, that I can tell yet that, if you pick one species which is somehow closer to another species versus not. But that said, I think the part where I agree with you is the part where it's related to the number of true labels, that because if you even, I mean, this is just the mechanics of going through it. If I were to switch to, now this is where I get, because I have so many bookmarks, I'm kind of confused as to which one it actually, so give me a minute and I might give you a headache by switching rapidly between thoughts, because it says that it has to do with the question the mechanics help us to answer is something that is pointed to as how many positive labels. See here, got the right one, good thing. See, Lrap, and this is not, again, this is not label weighted label ranking average precision, it's just, this part is just the scikit-learn part. But what Lrap does is it averages over the samples. That's why it's important, whereas our eventual answer wants it to average over the labels. But barring that, it averages over the samples the answer to the following question. For each ground truth label, what fraction of higher ranked labels were true labels? And therefore, it seems to me that it wants you to somehow, in a multi-class label, have your probability rank ordered in the way that, that matters, meaning that you want the higher probability labels to be more true than your labels that are below where you're at. Actually, the best way of saying it is, again, returning to the verbiage of what question that it's trying to answer. For each ground truth label, what fraction of higher rank labels were true labels, right? And this performance, as he says, will be higher if you're able to give a better rank to the labels associated with each sample.
Is ground truth like multi one hot encoded, right?
Yes, yes.
So there's no ranking aspect in terms of the ground truth. So no one is saying that one bird call is more important than the second bird call.
Exactly. Yeah, or one species is more important than the other species.
Okay.
Yes.
I see.
Right. It's the same. But that said, it's like saying when I have multiple classes and let's say I come to the 5th class, which is also true, then how many of the 4 classes before it are also true?
Right. Okay.
That's where the label ranking comes in, right? Because
So
we
if you
rank
have,
the probabilities.
right. So if you have all those 5 correct, in actually whichever order they come, the score should be the same, right?
Yes. Yes.
Okay.
And also, as this says, right, if there is exactly one relevant label per sample, the label ranking average precision is equal to the mean reciprocal rank. And the mean reciprocal rank is just where it appears on the 20. So it's 1 by that. So for example, if a cat were to appear and in the 3rd position, then it's 1 by 3. In 2nd position, 1 by 2. The 1st position, 1 by 1. That's what the mean reciprocal rank turns out to be. Now, I think having gone through what we went through of the mechanics of calculation, then it makes it easier to understand the math here, because otherwise the math is very confusing. But having gone through it, and if you then know what this y of 0 and the dot, which means like the Lij, then once you understand what we just went through of the mechanics and then apply it here, then the equation becomes a lot simpler to understand. Okay, because basically this guy is just the second value that we calculated, the mechanics of the second value that we calculated. So it's the answer to the second question in the mechanics that we went through. And the second question is how many true labels there were until we reach the correct label. That's what this guy is. And then this first guy is how many labels does it get to the true class of interest, which is just a rank, right? Which is the first value when we went through the mechanics. So once you map this to the second question we answered from the Stack Overflow, and the bottom guy to the first, which is just, how many labels does it take to get to the one we are of interest, and this is just how many true labels there were until we reach the correct, then the rest of it becomes self-explanatory. And then obviously the averaging is the last paragraph of the Stack Overflow. So at least to me, it helped understanding that description and the mechanics, and then mapping the mechanics to the equation. Right. And then if you want to understand what is mean reciprocal rank, you can click on it and figure that out. But that still leaves me the question of, and here's one potential answer. I didn't want to bias people by giving my thought, but here's one potential answer I thought of the labeling is, I was thinking, again, this pure speculation on my part. I didn't find anything which backs this up, but is it a case of, if you have label ranking, does it provide some level of ability to say downstream that, some kind of thresholding, or basically, if I'm able to detect so many species, then that's good enough. And then when I go beyond that, then my accuracy suffers. So I'm going to lop it off. How I would go about doing that using label ranking is still unclear to me. And it's kind of like a fuzzy thought. I still have to think more about it, but that was one potential, maybe even a shot in the dark as to why this particular approach is preferred. But, it's an open question to me of why this metric. And if anybody has, and as you engage and think about it, if you have good answers to this question, I am all ears. But, I just thought I would spend a little time to get a better understanding of what the Lrap metric is, which is label ranked average precision, and then go to label weighted label rank average precision, which is kind of what we want. As you see, Lrap has samples, and then in fact, if it's this guy or the next guy who basically says, okay, here is the modification that's needed to go from Lrap to the label weighted label ranked average precision. Give me a second. Not this guy. Okay, yeah, I think this guy. So this is sklearn documentation, this first part. And then he kind of explains, if you will, and you can map this to the mechanics that we went through, because basically he's saying fraction of labels scored at least as high that are indeed positive, which is another way of saying count the number of how many true labels there are until we reach the correct label, which is our second or the third step after we have ranked in our mechanics. And then obviously, and then see here is the label weighted Lrap. And then, there you just, instead of doing the sampling averaging, you do the label averaging across the samples. Okay, so, and I'll kind of post links to these so people can quickly chase the explanations now. Any comments, thoughts on this before we move to kind of pointers on just becoming a little smarter on sound processing?
So this metric is used as the loss function too?
No,
No,
I
okay.
believe not. It's just the metric by which the model is judged.
So can you explain again why this metric is used?
Don't have a good explanation, Dinesh. That's kind of what I'm seeking the answer to as well.
Yeah, so it looks like if you even recognize the sound, but if you rank them, the order is wrong, you get penalized for this. So that means you need to recognize the sound, but the order need to be right.
Not really right, from what Raquel and I were discussing as well. As long as the count of the labels ahead of where your label is fine, meaning the count of true labels, then you're okay. The order doesn't matter. Right, because the labels, because it's the fraction, it's only when you screw up to where something is in some sample is in the ground truth and you have completely failed to recognize it, that the model will penalize you, or at least the metric will become poorer. As long as you have labels which are true, then ahead of whatever label you're at and stuff, right? And we saw that question that we were trying to answer, then I don't think it matters. So which is what Raquel was pointing out too, right? That, as long as your true labels are all, the fraction of true labels ahead of the where you are at for the true label is what matters for the count. So it doesn't penalize you for that, the best I can tell, the metric.
Yeah, but when we did the simple example of this cat, dog, and bird, when the cat was on a second position, then we got the 0.5 rather than just 100% for that. In a simple, like here in a simple example, I think it was above is the top line. Yeah. So you see the score, we got the half because it was the cat was the order of recognizing of a cat was on a second position rather than on a first position. We did the score is 0.8, but it's the position is 2, so we got half the points, not the full.
Yeah,
Isn't it?
that is correct. But in that case, the issue, as I see it, is there's only cat, and you're predicting that something else is there in it.
Yeah, but okay.
So that's slightly different, right? Because there is only cat in the image, and you're saying that there is actually a dog and a cat.
Okay.
Okay. Whereas if there are multiple things in the image, as long as they all show up, then you don't get penalized. But if you are going to say that something exists in the image that doesn't exist ahead of something that actually exists, then yes, the metric is going to penalize you.
Okay, so in a sense, okay, I get it. So in a sense, so when it goes down to a multi-class, all it matters is like if you recognize all of them,
yes,
then you're okay. But if you give any value or any score to non-existing,
that's my understanding of. But again, I'm also working through the examples, but that's the difference I see.
Okay.
Any other comments or thoughts on this? I just thought it was a very new thing and an interesting difference, and I kind of poked around to see when would you use it or what, and I didn't quite. Of course, I didn't do a very exhaustive search, but so if people have thoughts or have worked through as you spend the next week, that would be a very interesting thing, at least for me, to know when and for what purpose is this a good metric in comparison to other metrics that you would use for a multi-class classification.
I have a thought. Can you hear me?
Yes.
Yeah. So I had a thought. So it's more like on the competition itself. So let's say I'm an ornithologist and I want to like find birds, and I have hours and days of sound. I would probably not have like a standard samples like this. I would probably like first find pieces where where you can actually hear the sounds, like very distinct bird sound or sound like that I care about, and then would classify them. So I'll have like two different problems to solve. One is like find something versus noise, and then try to classify noise. But I think like that. So here, because they wanted to have like a sort of standard way of approaching this, they split like those hours and hours of data into like more or less standard like pieces, so you don't have like that. You don't have like this infinite space. So maybe that's why you would need kind of this complex label. Like if I was solving this problem in reality, I would just find all the pieces of like separate sound, and then just maybe would deal with the fact that you can hear 2 or 3 sounds at the same time. You may have like 2 or 3 birds at the same time, even like in the same time frame. So then you might have like an easier metric that you can use just to find that there are more than one. So look, the point I'm trying to make is that maybe the label is complex maybe the metric is complex because the problem is somewhat artificial, right? You had standard piece of standard duration of sample where you need to find something, and so you need to kind of classify nothing versus something.
Yeah, except you read the one thing in the process of chasing this down. I also found, and I'll again post all these links, but there's like, actually that might not be the right one. Here, this is the right one. There's a whole bunch of metrics that apparently are used for label ranking. And label ranking itself seems to be a fairly common thing. I haven't figured out why. Maybe some other people can speak to that. I didn't chase that rat hole. But again, you see evaluation metrics for ranking problems, and there's like a whole list of them. And that is something that says that this that average precision, as you can see, is fairly common. And then label ranking average precision is just a rank of the labels. What is somewhat unique is this label weighted label rank, but even that, I subsequent to this particular issue or challenge, I've begun to see that it's not all that uncommon. So, but your thought is still valid that maybe it is the your point is the nature of the Kaggle problem setup is what necessitates that particular metric, maybe.
Yeah, actually, I think I want to clarify kind of after I thought a little bit. So in reality, you do have like multi-label in let's say you're solving like the bigger problem, but it's not as common as here, right? So here, let's say you have a 10-minute window, you'll have different birds singing. If you solve a different problem, you first do sort of segmentation and find those sounds, interesting sounds, and then try to do classification. Then you can still have like multiple birds singing, but that's a very different problem, right? And you don't see it that often, or maybe you do, but it's again, it's a different problem than finding like multiple birds in the same sample duration.
Yeah, possible. Okay, one last call. Any further comments or thoughts? If not, we move away from the metrics. And by the way, request to anybody on the call and otherwise, please continue to pursue this. And if you have any good answers or insights come to you as you work on the problem some more, please do share them. Just post it on Slack or speak up when we meet, so all of us become smarter about why or why not, or what's unique about this metric and why that's appropriate here compared to other similar metrics of multi-label. Okay, with that said, the other thing I wanted to point to, little bit before we are done for the call, is just at least the introductory bits and pieces that I was able to collect or gather from various notebooks and otherwise of the basics of sound processing. So none of this, again, if you are already familiar with it, it may not be a big deal, but at least for me, it's important to use the opportunity to become very familiar with the terminology, with the tools that I used, as well as, and again, it's an ocean, so you can drown yourself in it. But all I want is a basic familiarity and some good pointers to resources that I can use. So one of them a couple of them that I found and, that I'd like to point to. And there are many more. I'll share 3, 4, 5 more of it. But the first one that I thought was very useful was this write-up on just very basics of understanding the audio data, then taking you to Fourier transform, then what's the FFT, what's a spectrogram, and then, of course, related to speech. Now, most audio related posts have to do with speech, which in our case is not quite applicable, but a lot of the principles are the same. So if I can get my laptop driver, graphics driver to cooperate. There we go. Oh, maybe I spoke too soon. Okay, here, understanding audio data, Fourier transform, FFT, and spectrogram features. So again, I'm not, in the interest of time, going to take you through all this, but this Librosa is something which, again, it's a Python library that I believe is very handy. Many of the folks, at least, again, as I poke around in the Kaggle stuff and otherwise, seem to rely on it while working on audio data. And if you're interested in the guy who developed it, and of course it's dated, it's about 6 years old by now, so there's probably a lot more recent stuff, but here's a YouTube video of the guy presenting about Librosa at the SciPy conference, and I'll post that link as well. So you can kind of begin to understand how to process sound, what's the basics of sound and amplitude versus time, and then what that has to do with the frequency domain and how you take a sound wave, which is amplitude versus time plotting, which is what, for example, this picture, if it comes up, shows, and how you translate that into frequency versus time. So this is, using Librosa to show the amplitude of a sound wave versus time, and it's time domain, and then you use Fourier transform in order to transform every amplitude and then take it to the frequency domain and figure out what frequencies make up the sound wave or the wave that you're seeing. And then this guy takes you through a fairly good explanation of what that looks like and what FFT is, and then also what is a spectrogram. And if you want to begin even further through the basics of what a sound wave is and stuff, he has another post which talks about the basics of sound waves that every data scientist should know. And again, I think that's also a good post, since it starts with very fundamentals. If you don't have an electronic or an electrical engineering or have otherwise not been exposed to sound waves. So this talks about waves, how sound is processed, how it is generated, how it's recorded, what's pulse code modulation. And you can see that in our current competition, it says, for example, that the FLAC files are, if I remember correctly, 16-bit PCM. Somebody correct me if I'm wrong, but so again, what does that mean? What does the sampling rate or sampling frequency mean? And why is, what's the Nyquist theorem? These are things that WEs or electrical engineers or people who are filled with sound are familiar with, but it's good to get at least familiar with, even if you're not deeply an expert in this. But again, and then the various forms that or various file types and audio codecs and ways for storing sounds. And then in fact, one of this free lossless audio codec is the FLAC files that we find in our competition, right? So these two links I thought are very helpful and in kind of bootstrapping you towards audio processing and becoming familiar with audio. The other, there's also another SciPy talk that I'll post a link to, which is basics of sound processing with Python. And that's something that's useful as well. And I'll stop sharing for a minute here. There's one other link that I wanted to point to. That I thought was extraordinarily, and that guy is, I think many of you will already be familiar with 3 blue, 1 brown videos. And he has an exceptional video. Even if you're an electrical engineer and or played with sound, he has an exceptional video discussing what is a Fourier transform and giving you an intuition for it that I think minus the math, which is just visual and extraordinarily insightful. So I'll post that as well. And the other thing that you'll see besides Fourier transform is, I think, very soon after that, and I think this was used by Steve in the notebook that he was using, is the short-term Fourier transformer, STFT. And there are some videos that are available as to what they do and how they work. So there's a whole list of things that are related to sound processing and the details of sound. In the interest of time, I will not take you through all of it, but I would encourage all of you to kind of become familiar with it, or at least browse through it if you're already familiar with it, to just bootstrap yourself about the details of sound and sound processing, because at least for me, all these links helped get me familiar with the terminology and with what it is that we are setting out to do when we process sound. And again, as I said in the beginning, at least I like to use any of these competitions to become familiar with the domain as much as with the specifics of the competition. So I'll post all those links for those of you interested, and feel free to go through them. I mean, it takes time and effort to go through it, but I think it's worth it because it gives you a much better understanding of what what we are actually setting out to do, and instead of just kind of just slap things together, get to a spectrogram, run a convolutional network on it, and out pops the results. But gain an understanding of the process we go through. Any comments or anything that else that people want to share? Any pointers or any comments on sound processing, or have anybody already familiar with this space who wants to share their thoughts?
Just posted something from, I think, let me post that link again.
You want to share? I stop sharing. So.
We can probably catch on next time. I was just going to say that if we have time, the same thing that you did with your example of cat, dog, bird, with ground truths and probabilities that are predicted.
Yes.
We should probably try calculating average precision as well as this Lrap and see how much of a difference it is. Maybe that'll point us to like why one is better than the other, or what one catches better than the other.
Yeah, that in fact, to your point, because if you're pointing to the
he makes a statement where he says this metric is related to average precision but uses label ranking instead of precision and recall. And he says Lrap is basically asks the question that for each of the given samples, what percentage of the higher rank labels were true labels?
Yeah, that's essentially what I had pointed to
right.
In that thing, right? Yeah.
Yep.
Yeah, because I had also bookmarked that, I think, the link, but yes. So like you said, if we, kind of get...
Yeah, the score for each sample, then we can kind of see like what one is predicting better. I mean, where the loss is becoming more or less. Maybe that can point us to like,
yeah, or where the metric. Yeah, because this still is in the loss. Just the metric.
Right.
Yeah. Yep. Yeah, that's, I mean, I read exactly what it says, but like you said, I at least until you get the intuition, they're just a bunch of words, right?
Yeah, since both are in scikit-learn, it should be pretty easy to like get those values out and then see, okay, in this ground truth label, when the label is this order, because average precision is kind of doing the same thing, it's just not ranking, right?
Yeah,
you're picking the highest probabilities, and then that's what you're using for calculating your stuff. So,
yeah, I didn't have the time to.
Yeah, I'll see if I can pull that up next time, and if at all there is anything intuitive that I can understand.
Yeah, that'd be great. Thanks. Okay, any and oh, by the way, there's also links that I bookmarked having to do with augmentation in the sound domain that I'll also share. And there are people who have set up GitHubs where they've kind of followed the albumentation examples for images to augment sound. Whether we need it, I don't know yet in this competition, but just following me initially, let's just go broad and see what all exists, and then we'll dive into the details of solving the problem. So that's kind of what I had planned to share, and probably next time we can get into details of actual EDA on the competition and looking at the spectrogram and all that, because I'm assuming by then, at least my request would be for many of you to go through some of these sound audio introductions and files, so we know what we're talking about when we go through spectrogram or MEL spectrogram or things like that. So at least there's some level of comfort with what it's meant by those things and what they represent with respect to the audio, or why we go from time to frequency domain and things like that, and what again we do when we do the FFT or STFT and stuff. So that would be my request to people as we get into the competition. Of course, you can forget all this and start running notebooks that are already there, but I think this helps understand what we are going through as well. Any comments from anyone else before we call it done?
There's just a new Kaggle competition started 2 days ago on bird identification. And so like within the discussion of that, there's like a few people asking about how you get started with audio stuff. So I've just posted in the chat a couple of notebooks that describe how to sort of begin processing with audio from that.
Great. Thanks, Steve. Okay. If not, hopefully, please spend some time, as Steve mentioned last week as well, playing with doing some EDA on the data and trying to submit. That way you'll at least be familiar with the problem, and also feel free to raise any issues you have with any of the submission challenges. And that is what makes it worthwhile. Thanks, everybody. Have a good rest of the week or weekend.
Cheers, thanks.
Bye.
Thank you.
Bye.
Thank you.
Yep.
Thanks.